Okay? So to get openness, it's all about what portion of an arc length we're cutting off from the circle, what fraction of its circumference. Okay, so then what's degree measure? So thinking about that, what is degree measure? Ahmed. So if measuring angles is about getting a fraction of the circle, then what's degree measure? Can you explain it? Okay, Janet. Say it again. Right, so she's getting a fraction of 360, right? So if in degrees, all the way around a circle is 360, so we're taking fractions of 360. So every degree of openness is how much of a circle? Every 1 degree of openness that we get, 1/360th, right? Every 1 degree of openness corresponds to 1/360th of the circumference. And then what about radians? So that's where we left off last time. What is radians? Yeah, Peter. Okay, we're using the radius now. So radian measure uses the radius. And what do? We take that radius and we... Travis.
We find the length of the portion of the circumference that equals the length of the radius.
Okay.
And then that out the length of that portion out of the whole circumference length becomes the fraction.
Good. Okay. We saw that if you zoom out here. We saw that if we took the radius and put it on the circle, but then did that for for different circles, what happened? So these are all 1 radius length, right? These are all 1 radius length wrapped on their circle. What happened? What do we see? This is 1 radius length wrapped on its circle. This is 1 radius wrapped on its circle. This is 1 radius wrapped on its circle. Yeah, and so they all are the same fraction of a whole circumference. And so we can use radius lengths then to measure angles, and that's what radians is. So, okay, so this angle that cuts off 1 radius length, no matter how big the circle is, it's always 1 radius length. That angle is, what angle is that? 1 radian of openness. 1 radian of openness. Okay, so here's just another review of this. Radian angle measure. An angle whose rays subtend an arc of, so this one is subtending 1.2 radius lengths. So each of these pink arcs is 1.2 radius lengths. What's the openness of that angle? Patty? 1.2 radians. You see? That's where the openness in radians comes from. How many radius lengths the angle cuts off. Okay? So can you maybe estimate this one? So, is that circular? Yeah. Close enough. All right, so see if you can kind of make an estimate of, and I'm talking about the angle on the left, so this openness to the left here. Estimate how many radians that is. Go. Talk to the person next to you. The left. Openings to the left.
1 less than 13 then. The radius length would be greater than 90. But it's not 180. It's not.
Okay, so so in your mind, what are you trying to do to answer this question? What are you trying to do to answer this question of what the openness in radians is? Joseph? Not sure? Hayden? And so what do you do? So explain what you're doing to get that number 2.5. You're guesstimating what? A third of the circle. How do you know a third of the circle is 2.5? Guessing. Alex? No, we don't know anything about 2 pi. How do we get an openness? How do we measure this openness? We don't know anything about 2 pi. Okay, so you're guessing it's what?
2.
He wants 2. And you're looking at the radius, and you're going to do what? Put it on the arc length. So he thinks about 2 of these. Agree? More or less? Maybe a little bit more. Right? Yeah, around 2, maybe a little more. So we're taking the radius, and then we're wrapping it on its respective circle and saying how many of those radiuses go around there. So maybe this is, maybe 2.3. Okay, one more time. Go. So this is the small angle, the small amount of openness here. So how many radians do you think that is? Okay, Renee, you got a guess? And why a quarter? Okay. Where am I? So, how about, can I use the largest circle? Is that okay? Does it matter what circle I pick? So I'm going to take the largest circle, and then you're saying what? Wrap it around the outside. So if I started here, and I wrapped it around the outside, it might go to about here. And so then why'd you say a quarter? So you're looking at this right here? So she's saying this is about a quarter of one radius length. Does it make sense? What we're doing here?
Makes sense.
Good. How about the rest of you? No. Where did I lose you? We're taking the radius of the circle and wrapping it on the circle and then counting how far around the circle we go. So if I take this radius right here from here to here and I wrap it on the circle, it would go about this far. Is that right? So then that amount of openness is now a fraction of it, and maybe it's about 1/4 of the radius. See that? So this openness right here is about 1/4 of a radius. So it's 0.25 radians of openness. Better. Yeah, Jessica.
How do you know which radius to measure from?
Okay, how do you know which radius to measure from? So in this one I picked the smallest, and this one I picked the largest.
Does it matter?
Does it matter? Doesn't matter.
So we know.
Yeah, because so look, this is one radius length on its circle. This is one on its circle, and this is one on its circle.
So you just want it just to be like.
Just yeah, to show that very fact that you asked about. Yeah, that any circle that you drew here, you'd get one, and the openness would be one radius length on its respective circle. Okay, so remember, just a review, quick review. We said that this is our initial side, conventionally, of the angle. It's called the 3 o'clock position. Positive opening angles open this way. So this is counterclockwise, is a positive measure of openness. So counterclockwise, negative. If you open the angle of this, starting here this way, that's considered a negative angle. Okay, this is the terminal side. Okay, so this circle of radius 1 is called the unit circle. Unit circle has radius 1 and center at the origin. So the unit circle is a very important, we work a lot with the unit circle, and the reason is because every circle that you could imagine, every circle in the whole universe, can be thought of as the unit circle. So for instance, a circle of radius, doesn't matter, 24 feet. Okay, so this is 24 foot radius. How can that be thought of, this circle of 24 feet? We're going to make something in our backyard, some garden or something. In our backyard, 24 foot radius circle. How can it be thought of as the unit circle? Radius 1. How can it be conceived as a circle with radius 1? Any ideas? Abdullah? Yeah, and so what would the 1 represent? That's right. So what would 1 mean in this case? Yeah, so 1 would be 24 feet, or 1, what? Yeah, 1 radius length, you see? 1 radius. So in this case, our circle is 24 feet, but that 24 feet is 1 radius. It's 1 radius. So up here, this number right here, 0.5, is signifying what? 12, because it's 0.5, half of a radius. So by 0.5, we're not saying 0.5 feet, we're saying 0.5 of a radius. So that would be our 12 feet. You see? So you can handle any circle that way. That way, any circle you talk about, you can think of as the unit circle, where so 1 is whatever its radius is, 1 radius. And so then the scale from 0 to 1 is whatever fraction of the radius. Okay, so that's why we emphasize so much the unit circle, because any circle in the whole universe, no matter what, so 0.2 miles. So a circle of radius 0.2 miles can be thought of as the unit circle. How? What does the 1 mean? That 1 is 1 what?
Radius.
1 radius length, but now our radius length is 0.2 miles. Okay, so that's the idea of the unit circle. Okay, so here are I'm marking off whole numbers of radius lengths. So that's one radius length, or an openness of 1 radian, right? There's 2 radius lengths, 2 radians. 3. There's 3. There's 4. So all I'm doing is I'm just laying that many radiuses on the circle, and the corresponding openness is that many radians. It's the same value. It's the same value, the number of radius lengths cut off, and the openness of the angle is the same numerical value. Okay, so what I want you to do is estimate these angles. 2.5 radians, 0.3, 4.25, 6.1, -1, and -5. So can you estimate those angles given our basic unit circle here, and I'm marking off the whole numbers of positive radians? Go, talk it out. And yeah. No, radians. They say radians, right?
Okay.
So not degrees.
Okay, thank you.
Yeah.
Just to make sure.
So those angles. Radians. So like a visual, right? So it's like they're drawing a picture. So it's like you're drawing a picture. You're drawing the picture for those numbers of radians. Like draw the angle. Or pick the point find the point on the circle that would correspond to where the terminal side ends up. How about that? So is that more clear? Okay, so with the unit circle and talking about angles, we define what's called the quadrants. So the first quadrant is for angles in this first quarter, and then second, third, fourth. So as you go around counterclockwise, you just count first, second, third, fourth quadrant. And so this is going to help you to answer these. So Chungyang, where's Chungyang? How about the 2.5 radians? Where's the terminal side for that? You don't know? Well, where's 2 radians? Do you know where 2 radians is? The terminal side for 2 radians? Matthew?
Would be in the second quadrant.
Okay, where in the second quadrant? For the beginning, the middle, the end?
In the middle.
The middle of the second quadrant, 2.5. What do you think? Yeah, so it's going to be halfway between 2 and 3. That's 2.5 radians, 2.5 radius lengths. 0.3. Where's 0.3 radians going to be? Arturo. First quadrant. Beginning, middle, or end? So like towards the beginning, towards the middle, or towards the end? Beginning. Okay? So this much right here is 1/3 of a radius, or 0.3 of a radius length. So that's 0.03 radians. All right, what about -1? So that's 6 right there. What about -1? -1 radians. Let's get to that. Alec, this Alec back here. Yep, -1. Fourth quadrant? And how much openness do we go in the fourth quadrant? How would you figure that out? So maybe tell me where to stop. What's that? At this one? So we would stop there, is that right? Too far. So this, because this is really for 5 going the other way. So how can we figure out where 1 going this way is? Yeah, so it's kind of like symmetric with 1 in the positive one, right? It'd be this right there. You see? So that would be another. So it'd be 1 radius length, but going clockwise from 3 o'clock. Something like that. So something like that. From there, sweeping clockwise, that would be about 1 radius. And so then -5. Where would -5 be? So I would start here, and it would tell me where to stop for -5. Right there. If you thought right there, oops. Grab the pen. Okay, so right there. So it'd be how much open? So it'd be starting here, going clockwise, all the way around to there. That angle right there would be our -5. Okay, but there's like these whole numbers of radius lengths they're not advantageous. Okay, there's why is it? What's the kind of the disadvantage to these whole number of radius lengths? What do you see? Alec.
They're not really consistent with the axes. They're kind of one quadrant has one, some have two in different places than the other one.
Right, it's like they're not in useful places symmetrically, right? There's no symmetry to it. They just kind of end up in random places. They're exactly 1 radius length apart, but they just kind of end up wherever, right? So what would be convenient? It would be convenient to know like half of the circle or a quarter of the circle or all the way around the circle. So can you estimate, let's come back here. So if I come in here, what about half the circle? So let's zoom in here. Wow. What just happened? It just totally crashed. All right. Okay, we're back. All right, so we're zooming in here on the left side. And so this is showing, this is n of about 3.09 and then 3.19. So 3.09 is not far enough to get halfway around. And 3.19 is too many radius lengths. So what would you estimate how many radius lengths to get exactly halfway around? So 3.09, something between, or about halfway between 3.09 and 3.19. Oh, how'd you know that? All right, so what do you want to put in? 3.14159. Anybody know any more? 265? Nice guess. All right. So, and you know it. So, what number is that? Pi. Okay. So now many of you have worked with pi and formulas, and you've heard pi, and you said, "Oh, pi day," but maybe you never knew what pi was. What is pi? How would you describe what is that number pi about 3.1416? What does it mean? What is it? So number of radius lengths. How many times you'd have to wrap the radius on the arc length of the circle to get?
Half of the circle.
Exactly halfway around. That's what pi is. How many times you'd have to take the radius? Zoom back out. How many times you have to wrap the radius? There's 1, there's 2, there's 3, and a little bit more. How much a little bit more? 0.14159, right? So it's how many times you have to wrap the radius to get exactly halfway around. And this is nice because from that we can determine nice symmetric places on the circle. For instance, so what's exactly 1/4 of a circle?
Half of pi.
Pi over 2. Okay, what is 3/4 of a circle? So it would be like 1.5 pi, right? 1.5 pi. And so all the way around. 2 pi, which is approximately, so we often use 6.28, but that's not quite enough, but it's pretty close. Okay? Approximately 2 pi. Okay, what's 1/8 of a circle? So exactly half the openness to 1/4, or 1/8 of the circle. Pi over 4. All right, so looking at what 1 is, what would you estimate pi over 4 to be? So don't put in your calculator. Looking at what 1 radian is, what would you estimate pi over 4 to be? Like 0.8, right? So this is about 0.8 of the way to 1. So now find it. So now find pi over 4. We're thinking it's about it's a number. It's how many radius lengths, right? So we're thinking it's about 0.8 radius lengths. What is it? You're too slow. 0.785. Is that what you got? 0.785, and that's what we said, about 0.8. So what happens is you start working with these numbers with pi over 2, 3 pi over 4, 2 pi over 3, and you forget that what is that? That's a number of radius lengths. That's still a number of radius lengths swept counterclockwise from the 3 o'clock position. Okay? So let's do one more, like that. Oh. Okay, so estimate 1.5 pi, the bottom of the circle. Estimate, based on looking at number of radius lengths, what would you think that would be? Right there. What would you estimate 1.5 pi to be based on looking at whole numbers of radius lengths? Who's got a guess? Miles, what would you guess? How many radius lengths to get here based on the whole numbers of radius lengths? 1. Somebody else? Jack, what would you think? So here's 1, here's 2, here's 3, here's 4, and here's 5. So what would you estimate based on that? What would you estimate 1.5 to be? 4.75. Right? It's about about 3/4 of the way from 4 to 5, so 4.75. So find it. Once someone gets it, shout it out. What's 1.5 pi? 4.71. Very good guess. Okay, so what's the point? The point is, when we start working with these numbers that involve pi, don't forget that they are a number of radius lengths wrapped around the circle still. Okay? All right, so then the idea of fraction of a circle. So what fraction of a circle then is 1 radian? How would you find what fraction of the circle? 1 radian equals what fraction of the circle? Anybody? Get it there. So this is 1 radian. What fraction of the circle is that? Joe? 1 over. So let's get it exactly. What exactly? So what's the exact number of radians that's 1 circle all the way around? 2 pi. Okay, so 1 radian is, remember we said the basis of all angles is fraction of the circle. So 1 radian is, if we know that it's exactly pi halfway around, 2 pi all the way around, then 1 radian is 1 over 2 pi. And let's get that. So what percent is that of the circle? Uh, 0.159? About 0.159 or
15.9%.
15.9%. So how many degrees is 1 radian? How many degrees is 1 radian? What would you do? You've got everything you need. If 1 radian is 15.9% of the circle, then how many degrees is it? How'd you get that? Right, so we could just take this 15.9% of 360, and that would give us the same angle in degrees. So we take 0.159 times 360, and you say, tell me again? 57.3 degrees. So in terms of converting from, say, radians to degrees, or there's other systems of measuring angles, if you just do it in terms of percent of the circle, there's nothing to memorize. All you need to know is, in the given unit, you just need to know what 1 full circle is for your given unit, and then you can always find percent of the circle, and you never have to memorize any formulas. Okay? So some of you've memorized this formula for converting degrees to radians and converting radians to degrees, and it's your security blanket. You love that. Okay? But this is better because you never have to memorize anything, and it's based on understanding what's going on. The angles are based on percent or fraction of the circle. All right, so let's practice that. Does this make sense? All right, so let's go. Let's just do one. Okay, so here we are. So let's say we've got 180. So we'll do 200 degrees. So I'm looking over here. This is my degrees circle. So here's 200 degrees. And my question, what I want to know is, how many radians is that? So where do I start? I can take 200 degrees and find what? Oh. So 200 degrees is some fraction of a circle. What fraction or percent of a circle is it? So I'm going to start by going from degrees to percent of the circle. So find what percent of the circle, what fraction of the circle is 200. As soon as you get it, tell me.
Is it 3.55?
3 point, no, that's all right. What fraction of the circle is,
Oh, it's 0.55.
that sounds right. 0.55? Or what percent is that? 55 point, one more decimal place, 6. 55.6% or 0.55. Okay, so then from there, you got the percent of the circle. Radians is a piece of cake because you're going to take 55% of what? Right, take 55% of a full circle in radians. So we're going to take 0.55. 55% of 2 pi is? Someone said 3.49. Does that number make sense in our what we think of in terms of radians? How can you reason that that number seems right? How can you reason that 3.49 seems like the right answer? Yeah, that's right. A little bit more than pi. And then what are you seeing in the angle that matches that? So you're saying it's a little more than pi, and the angle is, the openness is? So she's saying it's a little bit greater than pi. That's correct. And how does that match what we're looking at here? The openness is?
Pi plus a number from pi
But
to...
what about the openness, the visual? How do you describe that, the visual? That Rachel? A little bit more than halfway, right? So pi is the half, it's exactly half a circle. The openness is a little bit more than that, so we would expect the value to be a little bit more than pi, and it is. Okay, gradients. What are gradients? I don't even remember. Let's look. Gradients is another way of measuring angles. All we need to know is how many gradients in one full circle, which is 400. Okay, so first I want find what 200 degrees is in gradients. The same angle, 200 degrees. What is it in gradients? Go. What is 200 degrees in gradients? Ginger, what would you do? Which we already had, right? So what are you doing when you multiply? What is that doing? Okay. And so, but why are you multiplying by 0.556? Right. So we want that percent of what?
400.
400. So we're going to take that same percent now. We were one step away. If all we needed to know was how many gradients was in a full circle, 400. So now we're going to take that same percent, and what do you get? 222? Okay, so I want you to find 15 gradients in degrees and radians. So if you had an angle measure of 15 gradients, so new problem, 15 gradients, or grads. How many degrees? And how many radians? If you understand what's going on, there's nothing to memorize. Okay? So 15 grads. How many degrees? How many radians? Is Jose here? Jose, tell me. Is 15 grads, is that a lot of openness, like compared to the circle, or just a little bit of openness? 15. 15 grads compared to a full rotation, full circumference, is 15 a lot of openness or just a little bit of openness? Okay, so right, so 15 is just going to be only maybe something like that. Jeez, look at it. Okay, so what are we going to do first? So what do we do first to answer this question? So I asked how many degrees in radians is 400 grads? So, yep, what first? Okay. Joseph,
You want to take 15 over 400?
why would you do that? What does that mean? Right, so we're going to come here first. Every other unit of measuring angles is based on percent of the circle. So you want to take 15 out of 400, and that gives you what percent of the circle? Did you get it? 3.75%. What's going on? Something like that. And then what? Keep going. You choose whatever you want.
For degrees, you take that answer and you multiply it by 360.
So you want 3.75% of 360. Is that right? So 0.0375. Oh, sorry. 0.00. 0.0375. Is that right? Times. And what'd you get? 13.5 degrees. What about the amount of openness? How much openness is it? Right, all of these are the same. They're all just different ways of measuring the same angle, same amount of openness. They're all 3.75% of the circle. This is just using degrees, 13.5 degrees. Okay, someone else. How about radians then? How would you do radians? Somebody new? Yeah, Danny.
So you take the fraction of the circle of the
15 over 400. Yep.
and you multiply that by 2 pi
We want 15 400ths of
of
2 pi. That's it. So we want that fraction of 2 pi because 2 pi is a full circle in radians. What's the openness? How much openness? Like this?
Oh no, it's each axis.
Same amount of openness, just a different way of measuring the same amount of openness. How many radians is it? More or less than 1? Less, because we know 1 is 1 radius wrapped on the circle, so it's going to be 1, like maybe a quarter or something. What does it end up being? 0.23 radians. So about 1/4 of 1 radius length wrapped on the circle. Okay, homework due Monday. Be safe this weekend. Yeah. There's other ways too. Like we could make up our own. We could say 1,000, 1,000 Sparkies is 1 circle, and then we could do the same thing again. Same fraction of 1,000.
Are you gonna have to
I might throw in investigation. I think I'm going to include also investigation 2, mod 7 investigation 2. We'll put that on there.